An orthonormal basis can be used to represent a set of n signals. In this video, we will see that the basis is not unique and that several alternative bases can be used to represent the same set of signals. We'll see it with an example. We have these four signals, S0, S1, S2, and S3, and this orthonormal basis of dimension 3 is able to represent each signal as a linear combination of these three elements. Therefore, every signal is represented by means of a vector, in this case a three-dimensional vector, which contains three coordinates: the coordinate with respect to phi 0, the coordinate with respect to phi 1, and the coordinate with respect to phi 2. And therefore, the four signals can be represented by this set of four three-dimensional vectors with the three coordinates with respect to the three elements of the basis. And it is possible to represent these coordinates in a three-dimensional picture like this one. This orthonormal basis allows the representation of this set of four signals. However, the basis is not unique. This is the basis that is obtained by applying the Gram-Schmidt orthogonalization procedure, processing sequentially S0, S1, S2, and S3 in this order. If we change the order of the signals, the basis will be different. And in some simple cases like this one, it's even possible to find an appropriate basis by visual inspection. It is straightforward to see that these four signals can be represented by using this three-dimensional basis. The coordinates of the different signals are given by the amplitudes of the signal in the three intervals between 0 and 1, 1 and 2, and 2 and 3. For instance, the vector representing S0 is given by 1, 1, and 0 because these are the three amplitudes that we have in the three intervals. The vector for the second signal is 1, minus 1, and 0. For the third signal is minus 1, plus 1, plus 1, and for the last signal is plus 1, plus 1, plus 1. It is straightforward to see that these four signals can be obtained by means of a linear combination of the three signals that we have in this alternative orthonormal basis. It is an orthonormal basis because given the definition of the inner product, it's straightforward to see that the elements are orthogonal because the signals are non-overlapping, and this product in the integral is going to be 0 for every pair of signals. And each signal has energy equal to 1. Therefore, we have an orthonormal basis. The four three-dimensional vectors representing the signals in the new basis can be also plotted in a three-dimensional picture like this one. The vector representation of signals in an orthonormal basis allows to compute the energy of the signals and the distance between every pair of signals, which is related with the energy of the difference between these signals. And remember that these measures, the energy and the distance, are very important in the design of a digital modulator because there are two parameters that must be taken into account in this design. And they can be computed by means of the vector representation. The energy of a signal is equal to the squared norm of the vector representation for this signal, the addition of the square of each coordinate for this representation. And the distance between signals corresponds to the Euclidean distance of the vector representation, the square root of the addition of the square difference coordinate by coordinate. Here we have the vector representation of these four signals in a given orthonormal basis, and here the vector representation of the same signals in a different basis, also orthonormal basis. And it's straightforward to see that the energy and the distance between signals using these expressions related with the vector representation is the same one independently of the orthonormal basis. For instance, the energy of the signal S3 can be obtained by adding the square of the coordinates. The square of the square root of 2, 2, plus the square of 1, 1 is 3, and 1, 1, and 1 to the square, we have 1 plus 1 plus 1 is equal to 3. In any case, it's straightforward to see that we have the same energy in both representations and that we have the same relative distances between signals using these two alternative representations in two orthonormal bases. If the norm of each vector and the relative distances between the different four vectors are maintained, this means that in the vector representation, in this case in a three-dimensional space, using the first basis, and in the representation of the four vectors obtained in the second basis, there is also a rotation. We have the same distance with respect to the origin, the same norm for every vector, and the same relative distances between points. We have only a rotated version of the representation that we have in the other bases.